In the last episode, we talked about our atmosphere, the structure of our air. But in our day-to-day life, we only experience a small portion of that gigantic system. One of the most common down-to-earth phenomena we all witness are storms. Thunders, lightning, wind, rain, hail, and snow. We've seen them all, but how do they actually work? Well, that's what we're here to find out. Hello, and welcome to 7 Facts. When looking out for storms, one only needs to look up at the sky. Those puffy white pillows of water might look harmless until they don't. We can all immediately recognize storm clouds on the horizon, and ever since the dawn of life, both man and beasts feared them. And for good reason. All storm clouds start out as harmless cumulus clouds, the ones we're all used to seeing. But these clouds can be fed, and when they do, they can turn into monsters. Air currents from the ground can lift huge amounts of warm air and a lot of humidity. Gradually, all this energy builds up, and sometimes cumulonimbus clouds are formed. Storm clouds. These clouds can be kilometers wide and reach up to 18 kilometers in height, literally holding 1,000,000 tons of water. There's enough energy in this system to power a small town with electricity for an entire year. Those air currents we talked about can now reach over 100 kilometers per hour, and all that friction generates electricity that whips and crackles the entire sky. Eventually, there's so much electricity that the clouds simply have to discharge the excess in the form of lightnings. Similarly, so much water can accumulate in storm clouds that eventually they just drop back to the ground in the form of heavy rainfalls. During such storms, winds can be powerful and deceiving. On June 24, 1975, Flight 66 of Eastern Airlines crashed at the JFK airport in New York while attempting to land. The reason? There was a thunderstorm going on, and a microburst of very fast winds actually pushed down the aircraft, killing 113 of the 124 people on board. We've gotten used to the safety and protection of our concrete buildings, and we've come to believe that the storms of Earth are not that big of a deal. But in fact, they're among the deadliest natural phenomena that occur on our planet. No storm is complete without its two buddies, lightning and thunder. But what are they, and how are they formed? A lightning can be a powerful thing. It can hold up to 100,000 amps at 1,000,000 volts. When discharged, that much electricity can instantly heat up the air to 30,000 degrees Celsius, creating an explosion we can hear as a thunder. That's right, thunders are literally the sound of air exploding. But what's up with all this electricity? Why do lightnings occur in the first place? As I said before, storms form when warm, humid air from the ground rises up into the upper atmosphere. When that warm air meets the much cooler layers from above, water vapors condense and form the harmless-looking cumulus clouds. If this process continues, these clouds morph into cumulonimbus clouds that get bigger and darker as the water droplets increase. Some droplets freeze and start rising, while others remain liquid, falling downwards. They constantly collide with each other, and all this friction causes static electricity to build up, essentially turning the cloud into a giant battery, with the cathode on top and the anode on the bottom. At first, electric arcs are formed within the cloud itself, but as the electric charge builds up, eventually that arc jumps to ground and lightning occurs. While it's easy enough to explain regular lightnings, there's one type that's yet to be explained. Actually, we're not even sure if it's a real thing or not. I'm talking about ball lightnings. This is a type of lightning that's been reported throughout history. It's usually a luminescent spherical object, sometimes as small as a pea, other times several meters in diameter. They occur mostly during thunderstorms, but last much longer than a regular lightning. They float and take irregular paths and shine with the brightness of a 100-watt light bulb. Sometimes they've been reported to explode after 10 to 15 seconds. If real, these are very rare occurrences and scientific data is scarce at best. Basically, our most reliable sources of data are eyewitness accounts, which isn't the best of sources. Currently, there are at least 17 different proposed scientific explanations for ball lightnings, so I guess it's gonna take a while before we figure this one out. Before we continue, I'd like to ask you something. This channel has no sponsors, so if you enjoy the content I make, please consider supporting these videos by becoming a patron. You can check out my Patreon page by clicking here or find the link in the description. And with that out of the way, we can move on to the next fact. Did you know that lightnings can leave a trace of their existence behind? They're called Fulgurites and are literally the scars of the earth after a lightning discharge. These weird-looking structures are vitrified silica and other debris. In other words, fused soil that turned to glass due to the immense heat of the electric discharge. Remember, lightnings can heat up their surroundings up to 30,000 degrees Celsius. Many times Fulgurites take intricate shapes as they follow the path of electricity dissipating into the ground. Fulgurites hold scientific value, of course, but they're also an opportunity to actually hold a lightning bolt in your hands. We're not done with lightnings yet. While they're extremely dangerous, can kill, destroy electric devices and even properties, they're also an essential part of our ecosystem and have beneficial effects. For one, lightnings create natural soil fertilizers. The intense heat forces a chemical reaction in the air that creates nitrogen oxides. These oxides are a natural fertilizer that falls and seeps into the ground along with rainwater. On average, about 15 million tons of nitrogen oxides are produced by lightning on Earth. Lightnings also produce forest fires. And while we generally perceive that as a negative thing, especially when those forests are not allowed to regrow, natural forest fires are actually beneficial for local ecosystems. The ash that's left behind is rich in minerals and also acts as a fertilizer, and the forest floor is cleared of layers of organic debris that would otherwise prevent nutrient circulation. And last but not least, lightning creates ozone. Ozone, or trioxygen, is a molecule of 3 oxygen atoms that, among other things, is very good at absorbing UV radiation. The heat produced by lightning forces oxygen molecules to bind together in this form and thus enrich our ozone layer. Okay, we've talked enough about lightning. What about hail? How does that happen? A hailstone is an irregular lump of ice that can fall from the sky, mostly during thunderstorms. Sometimes hailstones can reach huge sizes of over 15 centimeters and can be deadly, but most of the times they are much smaller than that. Even so, they can produce significant damage by destroying crops, killing small animals, or destroying properties. They form when vertical air currents force raindrops to move upwards. As they do, they reach low temperature layers where they freeze and increase in size. When this happens, they start falling again, but air currents from below again push them back up. This can happen several times until the hailstone is heavy enough to overcome the upward winds, and that's when it falls to the ground. Very rarely can a hailstone cause human fatalities, but they can cause severe injuries. So when there's a hail warning in your area, seek shelter. And if a storm approaches you and the clouds have a slight green color, you can bet your ass some hail is coming your way. Storms can also occur in the winter, and they mostly come in the blizzard variety. A blizzard can be extremely powerful too. These storms can deposit up to 40 million tons of snow and can have the energy of 120 nuclear bombs. However, blizzards are much more rare. winter times usually only bring some lovely snowfall. But have you ever wondered how snowflakes form or what it takes for snow to fall? At high altitudes, water vapor condenses into droplets of water. If the temperature is low enough, these tiny water droplets freeze and form small ice crystals. You can tell how cold the temperature is up there by looking at the shape of the snowflake. If it looks like a platelet or disk, temperatures were around -1 degree Celsius. At -9, they take the shape of columns, and at -15, they look like the crystal stars we all love. As these individual pieces of ice lump together, forming a snowflake, they get heavier and start falling towards the ground. And that's how we get snowfalls. I hope this video was interesting enough to have inspired you to look into it further on your own. If you liked it, leave a like and subscribe. You can leave your comments downstairs, and you can also check out my Patreon page if you want to support me. The link is in the description. I hope to see you next time. Bye.